I'm going to talk about whisperings of the city, characteristics and impacts of environmental shaking in the Taipei Metropolitan area. I'm Kate from National Taiwan Normal University. This project is mainly done by my students Ye Tingzhen, Chen Yaojie, and benefit from a collaboration with Chris Johnson in Los Alamos National Lab and Philip de Gong in Easter. Most importantly, the contribution from two local arrays. One is a Formosa Array with 5 kilometers spacing in the whole Taipei area, which was deployed and maintained by Lin Zhenhong, Lai Yajuan, and Shi Minhong. The other one is the building array in Taipei 101, deployed and maintained by Huang Wenji, Huang Boshou, Chen Guochen, Lin Qinren, and Gu Jinshang. In this talk, you are going to hear how much the nature and anthropogenic activities control the rhythms of the ground motion in the city, and how the traffic-induced shaking have an impact on high-rise building. So let me start with a question. Do you know how many types of seismic noise are taking place every day? They can be natural activities such as typhoon, rockfall, landslides. They can be human activities such as firework, vehicle, and many others. We all know that a better understanding of noise is crucial to improve the detections of small tectonic events, especially in populated areas. The Formosa Array, a dense broadband seismic array, was deployed in 2017. It has 140 stations with 5 kilometer spacing, which provides an excellent opportunity to study the characteristics, origin, and impact of urban seismic noise that is driven by numerous anthropogenic processes. This metropolitan area is located in a quaternary sediment-filled basin with low seismicity and composed of 4 geomorphological elements: the Western Foothill (WF), the Datun Volcanic Area (TV), the Taipei Basin (TB), the Linkou Tableland (LT). Here, the 140 seismic stations can be divided into 7 sub-areas, shown by different colored circles in the map. 15 of them are located in the city, shown by white circles. The spectrogram at a CT08 station shows a clear distinction in amplitude between day and night that occurs mainly in the range of 2 to 20 Hz. In the frequency band below 1 Hz, the highest energy is observed from 0.2 to 1 Hz and characterized by different recurring patterns. Higher frequency band, a daily recurrence, lower frequency band, several days. The spectrograms from sample stations in each sub-area shown here confirms 3 distinct frequency bands: greater than 2 Hz microtremor, mostly induced by human activity; 0.25 to 1 Hz secondary microseism, below 0.2 Hz primary microseism, mainly excited by oceanic gravity waves. So if you filter the continuous data into 3 separate frequency bands and plot the median amplitude for every day, and the resulting time series can be seen here. At frequency below 0.2 Hz, 7 subareas show very similar patterns in time also a very narrow range of amplitude. But in the city, it has the lowest median amplitude, which is reasonable given that the city, the basin, is relatively far from the coast. For 0.25 to 1 Hz in the bottom, we see also a very similar temporal pattern. But in this case, the largest amplitude is observed at CT stations, the green lines, which we suspect is associated with sag effects due to the thick basin sediments. Well, we will come back to this issue later. Comparing these two plots, you can say the median amplitude for below 1 Hz are mostly synchronized, suggesting that the source is a persistent disturbance across a large area. For higher frequency bands of 2 to 20 Hz, the stations outside the city exhibit a surprisingly similar time pattern with reduced amplitude comparing with the green lines that is observed in the city. In the city, they have much greater amplitude, more than several hundred times than the colored station, which is outside the city. The lower amplitude comes back every Sunday and reach the lowest during the Chinese New Year holiday. At the loudest station, so the CT stations, CT8, where a traffic roundabout is located within a distance of 400 meters, the 1 hour waveforms and spectrogram shows the repetitions of peak amplitude almost every 3 minutes. This coincides with the traffic signal cycle length for the intersection in Taipei City, which is 92 seconds stop, 92 second motion. And such correlation confirms the vehicle traffic is responsible for the higher than 2 Hz ground vibration. So the question next is, how much traffic-induced vibrations impact the tallest building in the city? The building array at Taipei 101 is operated by the Institutes of Earth Sciences Academia Sinica and has routinely recorded building vibrations. The building array team is listed here. The broadband seismometers were deployed on 90th and 74th floors, and also below ground on the B5 floor. This provides an unique opportunity to demonstrate the effects of traffic-induced vibration on the high-rise building. The acceleration spectra in 3 components at the station CT8 and the building array are compared here. We choose the quiet nighttime hours from 0 a.m. to 4 a.m. on December 5th, 2019. The spectral behaviors of B5 floor, the blue, is almost identical with CT8 red above 0.1 Hz, suggesting the common origins of ground and building vibration at higher than 0.1 Hz. The spectral amplitude at 74th and 90th floors, on the other hand, reveals multiple peaks at different oscillation modes of Taipei 101. The largest peak occurs at 0.15 Hz, corresponding to the first mode of the building. We found that the ground vibration recorded at CT8 revealed a clear synchronization at the B5 floor for 2 to 4 Hz in the midnight. At the 74th and the 90th floors, the temporal fluctuation in peak amplitude is less similar with CT8, except for the two highest peaks here. When the focused period increases from 1 hour to 24 hours, the hourly variation in peak amplitude for CT8, the blue, and the B5 floor, red, shows that in spite of the different amplitude, both of them reveal long-lasted, greater amplitude, roughly from 6 a.m. to 11 p.m. To further understand whether such hourly variation can be seen in higher floors, the power spectral density for fundamental frequencies of Taipei 101 at 0.15 Hz was obtained using 1 year continuous data in 2019 for statistically meaningful representation as shown here. The energy concentration appears to be more significant on 90th floor comparing with that on 74th floor, while the general pattern remains the same. That is, the amplitude remained stably high from roughly 9 a.m. to 8 p.m. We suspect that the jump in amplitude over 11 hours or maybe more may have something to do with the heavy traffic flow 1 kilometer away from the building. But what are the alternative explanations? In fact, the continuous vibrations of Taipei 101 has been explored to correlate with wind speed and temperature and to reveal strong seasonality. But here, we are talking about the hourly variation, not the daily variation. Given that the wind perturbation doesn't usually concentrate in a certain hours of the day, as denoted by the orange line here, to comparing with the ground vibration recorded in CT8, the gray bars at the background. Instead, it has recurrence intervals of several days, right? On the other hand, the temperature denoted by the white line here has sudden drop after and before noon. Highest temperature around noon, of course. What they say is that the temperature and the wind speed may not be responsible for the common variations of amplitude observed at CT8 and the Taipei 101. The dynamic interaction between the visitors and the variations of the Taipei 101 could be also excluded due to the business hour actually started much later at 11 a.m. instead of 8 a.m. when the vibration elevation started. Now, at the tops of the Taipei Basin, there is approximately 120 meter thick quaternary sedimentary layer that is characterized by very low VP and VS, leading to predominant frequencies of 0.4 to 1.8 Hz as shown by the right-hand side map. This provides an interpretation for the large amplitude of seismic waves in the secondary microseismic band 0.25 to 1 Hz for city stations, the green lines here. The predominant frequencies of 1 Hz is seen near CT8 station may also play a role to preserve parts of the traffic-induced signal. And that's probably why we only see the synchronized peaks at 2 to 4 Hz band as shown by the left panel, but not the higher frequency band 5 to 10 Hz seen to the right. In summary, By examining 140 stations in Taipei Metropolitan area, we explore 3 types of seismic noise characterized by 3 distinct frequency bands. In a relatively remote area, the microseismic bands reveal nearly identical patterns in time, suggesting the persistent oceanic or atmospheric perturbations across a large area. Human activities are responsible for the 2 to 20 Hz energy in the city. We discover that they are able to produce amplitudes of 2 to 1,500 times larger than nature sources. And finally, the small but repetitive ground vibration induced by traffic has considerable effect on the vibration behaviors of the high-rise building, such as Taipei 101, which encourages further investigation not only on the dynamic and continuous interaction between vehicles, roads, and buildings, but also the role of soft sediments on such interaction. That's all I have. Thank you.